I want to look at doing a problem where we have a mixture of gases. And when we have a mixture of gases, we take advantage of the fact that each of the individual gases behaves as if the other gas is not there. So for instance, in our mixture of 6 grams of oxygen and 9 grams of methane, the 6 grams of oxygen behaves as if the methane's not there, and vice versa for the methane. So we can treat each of them separately, and if we need to, we can add the contributions they make to the property we're looking at together at the end. And that's what we're going to do in this problem. What we're going to do is find the partial pressure of each gas and then the total pressure. Well, we find the partial pressure of each gas by, as I said, assuming that we have 6 grams of oxygen and not worrying about the methane, and then doing the same thing for the methane. So what we're saying, if we want to look at this a little bit more formally, is that this is not grabbing what I want. If we have a mixture of 3 gases, the pressure from the first one is given by the ideal gas law, taking into consideration just the first one. The second one, we just look at the moles of the second one. And for the third one, we can consider just the moles of the third one. Well, we only have 2 this time. One of them is oxygen. As we said, we have 6 grams of oxygen. We convert that to the number of moles, and that tells us that we have this many moles of oxygen. We can fill that into the ideal gas law and find that that gives us a partial pressure of 0.281 atmospheres for oxygen. We can do the same thing for methane, taking the number of grams of methane, converting that to moles, and then plugging into the ideal gas law to find that we have a partial pressure of 0.841 atmospheres for methane. And if we want to know the total pressure in the entire sample, it's the sum of the 2 partial pressures. 0.281 plus 0.841 gives us 1.122 atmospheres of pressure total.